Okay, so in our lab, when we combined the acid and the base and allowed a reaction to take place, the energy that the system gained came from the reaction giving up that energy. Okay, so it's an exothermic reaction. That heat of neutralization, we can also call that a heat of formation, because it's the heat required to form the products, is something that leads us to Hess's law. So let's talk about it. So Hess's law states that given any particular set of reactants that head to any particular set of products, your change in enthalpy, so that change in energy, is the same whether the reaction takes place all in one step, like we usually write them, or in several steps with certain extra gains of energy and losses of energy. But in the end, everything cancels out to being the same final change in enthalpy. Okay, so what's shown in the picture here, if you look at, if this was a time energy graph, there's the energy that the key thing that Hess's law is saying is here's your energy of your reactants, and here's your energy of your products. That change will stay the same regardless of if the reaction occurs over path A or path B. Okay, you can see that path B, there's a lot more going on. There's several different changes in energy. But in the end, the overall difference between reactants and products is the same. Okay? Whereas path A is just a straightforward going straight through that single energy change. This equation down here, okay, looks scary because of all of the crazy symbols and things like that. You probably recognize some of them from math. It's really not that bad. Okay? But let me define what those things stand for so that you can recognize it. Okay, so to discuss some of these symbols, there's the delta H with the little circle at the top, that's delta H naught. Okay, so that's just the symbol for the change in enthalpy of a reaction. The naught indicates that we're dealing with standard temperature and pressure. Okay, and we're not going to deal with anything other than standard temperature and pressure. Sigma, hopefully the crazy looking E, you remember from math class, that means sum. Okay, so we're going to be adding up all of the heats of formation of products when you see that sum. The N sub P and the N sub R. N is the symbol that when we have equations that involve moles, N represents moles. Okay, so N sub P is your moles of product, N sub R is your moles of reactant. Okay. Big thing here is to note that the number that we use for these, the multiplier, they come from your balanced equation. They're the coefficients. Okay. So like if this is your reaction, 2H2 plus O2 yields 2H2O, okay, these NP moles of product, mole number would be 2 for the water, and then for the NR moles of reactant, the mole number would be 2 for the hydrogen and 1 for the oxygen. Okay, it's just something that we have to multiply by the number of moles in the reaction. And then delta H naught F is the standard symbol to say heat of formation. Okay, and we get heat of formations off of a table. We in our lab, we calculated the heat of formation for that reaction, the ammonia and acetic acid reaction. Okay, so heat of formations, there's been people who have repeatedly run reactions and with better equipment than ours measured the change in energy and temperature to determine this, what we consider a constant heat of formation for that particular reaction. Okay, so again, this would be a giant table, nothing you need to memorize, something I will give you whatever heats of formations you would need for a test or a quiz. Okay, talking a little bit more about heat of formation. Again, it comes from a table. You'll be given these. All heats of formation, at least the ones that are in standard tables, are measured from combining elements. Okay, so like the heat of formation for water would be from that reaction that I showed you. Okay, 2 plus O2 yields H2O. It would almost look just like this, except it's combining the elements to make 1 mole of product. So what we would have to do here is actually reduce things. We would get rid of this 2, get rid of this 2, and then we'd have to put a 1/2 in front of our oxygen. And that's the actual reaction that the heat of formation of water comes from. Okay? Another example like that is the heat of formation for carbon dioxide. Same thing, in order to do it for just 1 mole, it's actually combining carbon and half an oxygen molecule to make carbon dioxide. Okay? But you'll know everything in the reactant area is elemental form. Okay? We don't, typically speaking, at least on the tables that have the standard heats of formation, they're not from reactions that start out from already compounds. It's always going to be the elemental form combining to make that product. Okay? Another thing is if you ever see an element in a reaction, okay? So say a combustion reaction where you have like C2H2 plus O2 yields water and carbon dioxide. And let's see, to balance that, based on my odd divisor of hydrogen on the left, I'm going to have to double this one. So I'll put a 2 here and a 4 there, which gives me 2, 8, 10 waters and 5 oxygens. But with this reaction, because there is elemental oxygen, the heat of formation, that's not going to, well, depending on your table, it may actually have it on there, but you would see a 0. Okay, so elemental pieces to a reaction always have a heat of formation of 0 because they're in their elemental form. It doesn't take any energy to get them there. They just naturally do it. Okay? So, couple of different ways that you can approach a Hess's law problem. So, here's a combustion reaction. These are very easy ones to do with Hess's law. First off, do make sure that your reaction is balanced. It doesn't work if it's not. And then, if you look up in a chart, depending on the table that you have, you may have heats of formation like this, where it gives you the reaction and how much it is. Okay? And many times, so that you can see the stepwise function and kind of what's actually happening reaction-wise, it helps. Now, to set this up correctly, right, there's a couple things that you have to do. You want to make sure that your heats of formation and the reactions that occur are going to cancel out and become what you see up top. Okay, so step 1, methane, CH4, must appear in the reactant side. So to do that, what you do is you'd actually rewrite your reaction as the reverse. But if we're reversing our reaction, what do you think that does to the energy? Okay, instead of being negative, okay, because the way this is, when you combine carbon and hydrogen to make methane, you give off 74.80 kilojoules of energy. Okay? However, and really, all of these are per mole, which is why these are always written to make 1 mole. But since we reverse our reaction, we have to reverse the sign on our energy. Okay, so that's first step, and that's going to get methane where we want it to be. Like that. Okay, so step 2, the next reaction, okay, if you set it up the way it is, that's going to put carbon dioxide where we want it to be on the product side. Plus, it's also going to help us a little bit. It's going to put oxygen on the reactant side, and it's going to cancel out our carbon that isn't in the final reaction. So we'd actually just leave the second one alone. Okay, so you can just copy it over and keep your negative 393.50. Alright, now, last step, we do have it set up correctly to be on the product side, the water. Okay, we want to get some more oxygen on the reactant side, and we also need to cancel out 2H2. Okay, so if you notice, we want 2 waters. We also need to add a whole oxygen, and we need to cancel out 2H2, so what you're going to do is you're going to take the whole thing, multiply it by 2. But when you do that, you also have to multiply the energy by 2. Okay, because instead of doing this for 1 mole of water, we're doing it for 2, so it's going to take twice as much energy. So when you do that, right, you get these numbers. And then you're going to be able to see that certain things will cancel out. The carbons cancel, okay? The two hydrogens cancel, and then everything else combines to make a reaction up here, okay? Once you have everything combined, you just take your numbers over here, add them together. So positive 74.8, negative 393.5, negative 571.66, and it gives you this amount of energy. This is one way you can apply a Hess's law problem. And depending on how you are given your heats of formation, this might be the necessary way, particularly if they give you heats of formation that aren't down to just 1 mole. Okay? All right, there is another way of doing it, using that equation from the beginning. Okay, and there needs to be ends in here. All right, what that equation tells you is that you're going to take your heats of formations of your products, and if there are any multiplier numbers in moles, any coefficients, you have to multiply by those. You're going to add them together. Okay, so we're going to do the carbon dioxide, which has a 1 in front of it, so there's no multiplier I need to apply there. But my products are going to be the negative 393.5 kilojoules plus my water, which does have a multiplier, so it's going to be 2 times your negative 285.83 kilojoules. Okay, and you combine that together, and then on the other side, you are going to subtract the sum of whatever your reactants are. Okay, in this case, so we're going to subtract. We have methane, which is negative 74.8. Okay, and then oxygen, since it's elemental, heat of formation is 0. So then that's the only number we actually have to subtract. So there, that looks a little better and typed out. So we have the 1 methane, the 2 waters added together for our products, and then we're subtracting the, carbon dioxide and 2 waters, and then we're subtracting the methane. And that gives you the same number that we got with the other way. Okay, so honestly, I find this way much easier, but it depends on the problem that you're given. Sometimes you're forced to have to do it the other way. Okay, depends on, honestly, what kind of heats of formation you're given. So, one other example of this is from our lab. We can confirm how close we were to reality here. So I looked up some heats of formation. These are not necessarily standard ones, but for my products, which were the ammonium acetate. All right, so you don't find heats of formation for ions, you only find them for what they would combine together to be. So my products are going to be negative 615 kilojoules per mole, and then the multiplier there is 1, so I don't need to really do anything. And then on my reactants, I'm going to have negative 80.8 kilojoules plus negative 483.5 kilojoules. Okay, and really what this would look like when I do my math would be negative 615 kilojoules minus negative 80.8 kilojoules plus negative 483.5 kilojoules, which gives you negative 50.7 kilojoules. So our lab, unfortunately, was not perfect, but there are a multitude of things that could have affected that. You know, we were trying to use a paper towel to make sure heat wasn't just escaping the calorimeter. There's whether or not we actually had the right molar amounts of both chemicals, and many other things that I'm sure you can think of. Okay, so what I want you to do is try this one. First, make sure you balance your equation. Okay, and then here are your heats of formations. And this one is set up so that you can do the simplified, just sum up your product heats of formations, your reactant heat of formations, and then it's products minus reactants. Okay, big hint to you, don't forget to multiply by the molar ratio numbers. Or those coefficients. Okay? That's probably going to be the easiest thing to forget when it comes down to doing these. Alright? So, on the Canvas quiz, this will probably be the last question, is your opportunity to put in an answer for this. And we will go over things in class tomorrow.